So today we will discuss our second homework. So first, a small lecture to introduce the homework. Okay, we have not talked about linear systems yet, but if you use Matlab, most likely you want to solve linear systems. So X is what we want to compute. A and B are our input matrices. And this is the dumb way of solving a linear system. This is what you don't want to do, but in MATLAB you can do it. What is the right way? It's to use the slash or backslash. This means that I want to divide B by the inverse of matrix A. In MATLAB you can compute X like this. Notice that this has nothing to do, absolutely nothing to do with computing the actual inverse and then multiplying these things out. And I want to demonstrate this. So let's start very easily. Rand of n b also rand of n, and we want to compute the solution of ax equals b in two different ways. So x1, actually, let's see, x1 equals inv of a times b, and x2 equals a over b. Okay. Now, these guys should be the solution of a linear system. Let's see if it's true. So if I solved this thing, it means that if I plug the matrix back in, so let's multiply these guys out, then I subtract b, this thing should be 0 or close to 0, right? And this is a small object. So it appears that I have computed the right thing. X2 looks better, at least for a 2 by 2. That's just a coincidence. If we go to, I think already 3 by 3. Okay, so this is the residual. It's called for the first. So for the first solution method, this is the residual for the second. Yes, there are some zeros, but there is no significant difference here in terms of error. Maybe. Okay, I don't want to say more. So it looks like I have computed the same thing. So how many of you are tempted to actually do this? And I ask, have I really computed the same thing? And well, by sheer coincidence, it looks like yes. This is really not the right way of looking at these objects, okay? So what is the better way of looking at these things? For instance, you can say how far are these two objects. Every time you want to measure the distance of vectors or matrices, it's much better to use the norm, of course. Maybe like this. Okay, these two objects are actually very close to one another. Likewise, it's not very useful to look at the actual residual. It's much better to quantify the size of the residual, and these residuals are very small. Okay, in both cases, these guys are very small. Okay, so it looks like both ways, both algorithms computed what we wanted to. Let's take a look very briefly at the cost of computing inverse of A times B versus the cost of solving this linear system. Anyone has any idea of how the inverse of a matrix is computed in practice? How to actually compute the inverse of a matrix? Anyone? Come on, everybody has, yeah?
You could just set the result to the identity and then perform your whatever decomposition you wish.
You can set the result to the identity. What does that mean?
Well, essentially, you want to compute the matrix multiplication that gives you the identity matrix.
Okay, linear system, you're saying. Any other idea? This is a good idea. Well, you guys should be familiar with Cramer's rule. If you have studied linear algebra, there is the smart way. Cramer's rule is a factorial algorithm in complexity, so don't even think about it. But apparently nobody thought about it, so it's fine. So what happens in practice to invert a matrix A, instead of solving this linear system, well, actually, yeah, it's the same thing. But what happens in practice is that A is a factor in two triangular matrices, L and U. Each one is inverted. These are triangular matrices, so you can invert them. There are algorithms for them. Once we have inverted these two guys, we have to multiply them together. So we have a gem, or if you can, it's a specialized gem. Gem is matrix multiplication. You have a specialized one because you are multiplying two matrices out. Okay, and all of that is just to compute A inverse. But what we want to do is actually A inverse times B. So after I have done that, I also have another gem. So in summary, yeah, I can leave it here.
What does gem stand for?
General matrix multiplication. In practice, what I have to do? I have to compute an LU factorization. This is n cube operations. I have to invert two triangular matrices. These are also n cube operations. I have to multiply the two triangular matrices together. And I have to multiply the result of that with B. Okay, what is the cost of this other approach? That other approach, what we're doing is AX equals B. We rewrite A as LU. Well, okay, let's leave it. LUX equals B. All right, we call this object, let's say, Y. So we solve Ly equals B. And once we're done with that, we have to go back. So we have an LU factorization, the same. And then we have two triangular systems. Okay, this thing is clearly faster, A. And in terms of accuracy, it's much better. The explanation of a faster, it's easy. The explanation of why the accuracy is better, it's not so easy, so I will skip it, but trust me. These are already a bunch of n cube reasons not to ever use the inverse. On top of that, there are a bunch of accuracy reasons never to use the inverse. Okay. Normally, if you are someone that inverts, that solves linear system like this, most likely you're also someone that asks these kind of questions. So try instead to look at things from this perspective. Whenever you want to compare things, you look at the norm. So for instance, if we want to see whether we really computed the right solution, we can put our solution back here. We multiply everything out, we subtract b, and then we don't ask ourselves whether the outcome is 0. That's not going to happen. Instead, we look at the norm. And if the norm is small enough, that's the way, then we're happy. That's the way to go. For completeness, I want to mention that these backslash and slash operators in Matlab are one of the most sophisticated operators. They are heavily, heavily overloaded. These things here, it appears that cover more than 1 million lines of codes. Why is that the case? Because basically they do anything you can think of. I didn't mention what this is. If you have to solve if instead of ax equals b, you want to solve xa equals b, now all of a sudden the inverse would appear on the other side of b, and then the notation for b for this would be that. So whenever you want to divide by some matrix, that's how you, let's say 3/2, that's easy, we divide by 2, and you can memorize the same thing. Here we want to divide by the matrix, and it would be like 3/2. We don't use that, but that's notation for solving this one here. Okay, so this is why there are 2 slashes, and these slashes do much more than solving linear systems. They actually look at the matrices, the matrix types, and they act accordingly. So they try to determine, first of all, they look at whether what you're trying to solve is actually a linear system or it's a least squares problem. What is the difference? Over here, I have A and B, same size. So, well, B doesn't matter. B could be 3/1 for that matter. But what I'm saying is that A is a square. So I have 3 equations in 3 unknowns. I could very easily set up a system where I have now I have 5 equations in 2 unknowns, and then I have a vector, my right-hand side has 5 components. This is not a linear system anymore. There is no guarantee that there exists a solution. In fact, very likely the solution doesn't exist. So what you can do instead is to approximate to find a solution that doesn't satisfy any of these equations, but minimizes the error in the square meaning. So this is called least squares, and you can solve these again like that. So this is the value that you would assign to the variable x and to the variable y. Notice that this does not solve any of these equations directly with the right-hand side b, but minimizes the error for all of them. And the notation is the same. So not only that, so not only does the backslash or slash decide whether you're solving a linear system of a least square problem, it looks at the structure of the matrix. If the matrix is a symmetric, some algorithm will be used. If the matrix is a symmetric and positive definite, some other algorithm is used. If the matrix is non-symmetric, other algorithms, and so on. And then, even more importantly, Matlab determines whether we are operating with sparse or dense matrices. And again, for those of you who actually are taking the class to do something with it, to use Matlab, the sparse word is probably very, very dear to you or important to you. So anyone has any idea what a sparse matrix is? Well, of course, you guys know because you took my last class. So, yeah?
With a lot of zeros in it.
With what?
With a lot of zeros in it.
Yes. So matrices with a lot of zeros are called sparse, but how many zeros? How many zeros do I have to have in a matrix to call it sparse? Sorry? That's again true, mostly, but mostly it's not a good definition. Sorry? No. Well, let me, oh, I have a hand. You took my class, you know that. Okay. What is, the answer is as many zeros as it becomes useful, convenient to exploit them. So let's say that I have a matrix. First of all, matrix, these are entries of my matrix. If there is an empty spot, it means that is a zero. Let's say that this matrix is 6 by 6. I would need 36 times size of whatever data type. Maybe I'm using doubles. This is the space necessary to store such a matrix, okay? If I define this matrix as a bidimensional array. But maybe I have so many zeros, so maybe I have only few entries different from zeros, so maybe it becomes convenient to store these entries individually. For instance, I could say in position 1, 1, there is whatever, 8, 1, 1, 1, 1. In position 1, 2, there is entry 1, 2. This thing here is a real number, is a double number. These things here are integer expressing where in the matrix there is something different from 0. Then would be, what is this? 4, 5, 1, 5, and so on. Notice that these 1 and 1 are integers, so they take less space than a double. There will be a point when storing a matrix like this becomes convenient over storing simply a bunch of doubles. Remember that when you store a matrix as a double, you don't have to keep track of where these numbers are. Everything is just in a row, and by what's the word? Convention, we have decided that our entries follow one another column after column. So we don't really have to say where we are relatively to the beginning. We just put all the entries one after another. But over here we have to specify actually. So we are in such position such and such, and the entry is. This is one of many different ways of storing a sparse matrix. It's just how Matlab stores it, so that's why I'm showing it. You can actually compress this data in many different ways. But this is only how to store a sparse matrix. More importantly is what you do with a sparse matrix. Maybe you want to multiply the matrix times a vector. At that point, you have to figure out whether it's easier to just go through one row of the matrix and multiply times the vector, or maybe if it's better to go step by step and just picking the entries that are different from 0. The access in memory is completely different. The storage is completely different, obviously. So depending on what you do with this matrix, and depending on what you do in this matrix, then the convenience comes sooner or later with the number of zeros. Just to give you an idea, in the real world, matrix that is 10% populated, so there are 90% zeros, it's really borderline. It's not yet considered sparse. Why is that the case? Because there are super optimized libraries, the BLAS, that are really, really fast for dense matrices. And so even if you only use one entry out of 10, it might still be convenient to store the matrix as dense. If you go to 1% of the entries being different from 0, then the matrix is clearly becoming sparse. Again, if you have matrices in real life, matrices of size 1,000,000, most likely your sparsity, your density is less than 0.1%. At that point, clearly you really want to store the matrix like this. And Matlab applies different algorithms depending on whether the matrices are sparse or dense. Just give you a very, very short demonstration of sparsity in Matlab. Sparse is a function to create sparse matrices, sparse objects. Let me just show you an easy way to look at the random matrix, at the sparse matrix. Okay, we know that the entries of M are all between a 0 and 1. Let's look, for instance, at the entries that are greater than 0.8. Okay, too few of them. 0.7. All right, they are a little bit sparse here and there. So now I can ask Matlab to find these entries, and these are the indices of by column. But if I pass you know how Matlab is, if you pass different number of entries, you get different objects. Okay, what do I have here? I have I being the x, the row coordinates of the entries that are different from 0. J being the y coordinates, and v being the values. So 1, it's easy because this matrix only contains ones, so that's easy. Now let's look at this thing here. It says 2, 1. And if we go and look in the matrix, in position 2, 1, oh, look at that, there is a 1. Next one is 3, probably 1, again, yes. So 3, 1, it's here, and so on. And this is a sparse representation of a matrix. So now I think I can do sparse I, J, V. That's how Matlab represents a sparse matrix. And if you solve linear systems again, or if you solve eigenvalue problems with these matrices, the algorithms are different. And you should familiarize with these in case you will use them. We will not touch anything with the sparse matrices. Just for you to see, SPI is a convenient way of visualizing a sparse matrix. It plots the pattern of the non-zero entries. There is a lot you can do with sparse matrices, just go through the documentation. Okay, enough for that. Let's get to the meat of this lecture. So, questions about this? No? All right. So, this is where most of the students freak out. So, pay attention. This topic is not as difficult as most of the students think it is, but it's also not as easy as the rest of the students think it is. So, try to pay attention. This is just a mathematical definition of a Fourier transform. It's one of the many definitions. I just want you guys to get the intuition behind of this. Let's say that you have a function defined in the real, on the real axis. It's a complex valued function, that doesn't matter. Just think of it as a function defined on the real axis. So for each value, for each real number, we associate a complex number. Okay. Let's think of it as a signal. What is a signal? It's something that goes on with time. And maybe it's periodic. It doesn't have to be periodic, but we think of it as periodic. And what we want to do is to represent this function as the sum, as a series, so the sum of many wave functions. And the wave functions that we consider as a base, they are fixed. So they are sines and cosines of different frequency. So what am I trying to do? I have a function and I want to represent it instead of as just f of x over the real axis. I want to represent it as an infinite sum of waves. That's what the Fourier transform does. It takes a function small f of x and it returns another function capital F, and what the capital F is, it's just a sequence, well, it's just a list of waves that appear in small f. This is the intuition. As you compute the Fourier transform of f and you get capital F, you can also compute the Fourier transform or the inverse transform of capital F and go back to your small f. Now, since we don't do well with infinite objects, we don't do well in the continuous world, there is the discrete counterpart. Discrete means finite. And so now we don't have a function anymore. We have just a number of sampling points. Our function has been, let's say, sampled, and we assume maybe it at equidistant points. And now I want to compute my Fourier transform, but I don't have a function anymore. I just have a sequence of points. And this is the formula that takes a vector of points and spits out the corresponding discrete Fourier transform. Okay, this is the intuition. Anybody lost so far? No. Almost lost, yeah?
Okay, so the Fourier transformation is the definition. Okay, and the xk thing, this is by definition as well?
Mm-hmm. Yes. So these points x, k are samples of the function small f of x on the real axis. That is the function, the functional definition in the continuous space. This is the definition in the discrete space. Mm-hmm. Okay, I told you what, over here, I told you what the discrete Fourier transform is. And from now on, we will talk about a fast way of actually computing the DFT. And that's what it's called, the fast Fourier transform. It's a fast way of computing this Fourier transform. This is one of the top 10 algorithms of the century. It's immensely useful, immensely widespread. And at the end of the day, what is it? It's nothing more than a matrix vector multiplication. Nothing more than that. X is my input vector. What is the input vector? Is this a sequence of points? You just think of them as a vector of points. F is a sum matrix. We will talk extensively about this matrix. And what you want to do is compute y. Okay? So the first question is, if everything that we do is a simply matrix vector multiplication, why do we even bother? We know how to do matrix vector multiplication, so what's the big deal? And the answer is, matrix vector multiplication takes n square operations, but this matrix here has an immense amount of structure, has many, many beautiful properties. If you exploit these properties, you can take down the complexity from n squared to n log n. And so the fast Fourier transform is the algorithm, it's one of the algorithms, that takes the complexity down and computes this vector y in a fast way. this is how the matrix f of m is defined. The entries of the entries I, j, they are hidden indices. The entries I, j are defined like that. The matrix is symmetric, and in Matlab you can compute a Fourier transform with f of t, inverse Fourier transform with I f of t. The shift I will explain later what this is. You will use it, yeah?
The indices of Fm are ij or kj?
Sorry, you're right. Yeah. I always make that mistake. I is actually the imaginary unit, yeah? Thank you. Most of your assignment is based around this recursive definition. So let's see if in the next 10 or 15 minutes you guys can digest this definition. You have to understand this to be able to solve the assignment, okay? This product here is called the Kronecker product. Don't freak out yet, I will explain everything. What this definition shows is, I want to compute a Fourier transform of size m. What does it mean? This is a matrix. I can express this matrix as the product of 4 matrices. Matrix 1, matrix 2, matrix 3, matrix 4. Notice that these products are the standard products, so all of these are known matrices to you guys. I will explain how to obtain this matrix. This is nothing more than a diagonal matrix. This is another object that is closely related to this one, very easy. And this is a thank you. You say it loud. Matrix. I don't know why today I don't speak English. And okay, let's see how to proceed. First of all, starting from right to left, I of m over k. Oops, I forgot. I chose to decompose m into 2 factors. Into 2 factors, k and m over k. So basically I'm splitting the size of this matrix into 2 as a product of 2 smaller integers. Of course, you can immediately say, what happens if m is a prime number? Well, guess what? You cannot apply this rule. So for the sake of your assignment, you will not use prime numbers, okay? So, starting from right to left, identity matrix. Everybody understands what this is. Identity of subscript k, it's a k by k matrix. Now, next object is a Fourier matrix. I have defined that already. This is exactly the same as before, it's just that it's smaller. What?
So the k you divide m with, and the k being the index are different k's, right?
Tricky here.
Okay, but that's not that bad.
Yeah.
The next question is, how do I calculate k? If m is 4, is k then 2? It's always the half of m, or what is k?
K, you fix k. K can be 2, then you would have I of m over 2, Kronecker product with f of 2. If you fix k.
M is given, and k...
M is the big one.
Yes,
and you
k
fix
can
k.
be one of many numbers, and I
Yeah.
decide for one.
Yep.
How do I decide for 1k?
You don't decide, it's arbitrary. What you have to do as an assignment is to make it work for any k. Okay, here I finally define the Kronecker product. Kronecker product takes 2 matrices and it puts them together like this. For each entry of the left matrix, you multiply, you attach the right matrix. So can you guys tell me the size of the A Kronecker B?
What is the size of B?
Haha, that's a very good question. So, you don't know.
So let's suppose if the size of B is x times y,
Yeah,
so the size of this matrix will be mx times ny.
perfect. So, the matrix B is repeated over and over. How many times is it repeated? It's repeated m times along the columns and n times along the rows. So in the end, this will be m times x, where x is the row number of B, by n times y, where y is the number of columns of B. So now you know what a Kronecker product is, and you cannot freak out anymore. Then we get to the diagonal matrix. Diagonal matrix is just a diagonal matrix. It cannot be too bad. Just as some structure, the first index of the diagonal matrix there, k, tells you that the matrix is composed of k different blocks along the diagonal. The first block is actually the identity. The second block is a sum diagonal small matrix, and then successive blocks are the powers of that diagonal matrix. And I am a nice guy, and I tell you what the block D looks like. So knowing this block, you can compute all the rest of the matrix. Yeah? No? What? What's confusing?
So D is also a matrix.
D is diagonal, yes, it's a matrix. This is Matlab notation. So it's a diagonal of these entries. So I get a diagonal matrix. And it appears k times along the diagonal. The first time it appears to the power of 0, which means identity. The second time appears as itself, then the square, then the third power, and so on.
But what size is D?
D is size m over k. That's actually easy, because if you have k times that, the overall matrix, you know that it's m by m, so it can only be m over k. Yes?
Each element is squared?
Each, over here, each element of the diagonal is squared, yes, and the next one, each element is to the third power, and so on. Yeah?
What do matrices K and M over K indicate?
K indicates how many times this block appears, a block being this guy here, and this thing indicates the size of the block. In a way, it's a little bit redundant, but I want it to be nice. Looks better? I see people nodding. Guys, don't hesitate to ask. It's your assignment, so you better understand this.
So I just don't understand, why does this perturbation come into picture?
Perturbation?
Yeah, this P matrix.
Oh, it's not perturbation, it's permutation. I will get to that.
Are the entries of 1D all the same?
No.
The entries of D are not all the same, they vary like this. So there is a J index, and J varies from 0 to m over k minus 1. So you plug J, you put 0, and you get one entry. You put 1, you get another entry. In the end, you get a vector. Diagonal of a vector, it's a matrix, it's a diagonal matrix, and you put this diagonal matrix on the diagonal. All right? Is it all right? No. Really, the diagonal matrix freaks you out so much?
No, that's easy enough to ask questions.
Ah, okay. I like this. So does it mean that over here you got, no, come on, so far so good, right? All of this is easy. Next, permutation, that's a word I couldn't figure out. Not perturbation, permutation. These guys, you might spend some time figuring this one out, so please pay attention to the picture. It's not so difficult after all. I explain this permutation by example. Let's say that we place a 2 over here. What this means is that we divide our matrix in two parts, and I put rows that are m over 2 away, I put them side by side. So the first row stays where it is, then I take the next row that is m over 2 away, and I move it up there. Then I go to the next, I put it here, and then I take the other one, and so on. Okay? Yes?
Is it, does a row have to have the same?
No, true. This is purely to show where goes what.
Okay.
This does not mean that this matrix, yeah, that means absolutely nothing like that. This is a general matrix. I'm just showing that this row here gets shifted, gets moved up there.
So it's not regardless of row.
Yes, it's a permutation. A permutation means that it doesn't alter the contents, it simply moves things around. I can also tell you, if you're not a linear algebra expert, when you multiply from left to the right, it means that you operate on the rows of a matrix. Permutation from left to the right means that you're only shuffling the rows. Permutation matrix is just the identity shuffled around. It means that this matrix here will have exactly n ones. All the rest of the matrix is zeros. There is only one 1 per column and only one 1 per row. So this is the identity matrix just shuffled around. Yep.
It have to be an even number.
Sorry?
M have to be an even number.
No, this is just by example. So for your assignment, you can assume that it's even, yes. And I specify this in the assignment actually to solve conflicts. Okay, and this is it for the introductions. So now I can read what you said.
You explained how you shuffle the rows around.
Yes,
But what rows do you shuffle around?
all of them.
Where does the values come from?
Where does the what?
Values.
The values comes from the recursive formula definition.
The P matrix just shuffles everything that's after the P matrix.
Yes, absolutely.
They work as well?
The P matrix shuffles everything that's after the P matrix.
So this is not the equality. This is not what the P matrix looks like. This is how the P matrix applied to a matrix performs, what it returns, okay?
And function.
Sorry?
And function.
No, it's an identity matrix.
It's a matrix product. P times this matrix returns this matrix.
What's the end of the recursion? So we have an f over.
So, ask me in 5 minutes, okay? That's a perfect question. Let's move on to the assignment. All right, let's get to the assignment first. So I want you guys to, oh, by the way, it's a team assignment. So you can do it yourself, by yourself if you want, or you can team up with your favorite mate. Part 1, 1D FFT. 1D FFT is exactly, precisely what I have explained so far. The input is a vector, in this case it's v, and the output is a vector, in this case y. And you have to compute f times v, not by brute force, but by exploiting the structure. So, let's see. Your goal is to write a Matlab function called my1dFft. Input is the vector, and here you go, this p integer, and p determines how the matrix is broken down. So p could be 2, could be 3, could be 5. In principle, it could be n over 2. I limit p between 1 and square. Oh, this should be less or equal to square root of n. Objective, elegant, as usual. This is not performance. We are doing Matlab, so we're not trying to attain high performance, but we want elegant and smart. What does a smart mean? It means low complexity. It means let's exploit the structure of the matrix. Sorry? No, you should compute y. I say it, yeah. So, and y must be computed by the recursive formula, okay, where the k is fixed to be p. So, this factor to decompose our matrix F is this number p. Of course, you might say, what happens if I set k to 2 and I only have an odd vector? Well, I tell you pad, so add extra zeros in the end so that you get to a stage where your vector is actually a multiple of p. Did you get that? No. Let me show you. I do it in practice. Okay, I want to compute f of v. V happens to be a vector with 10 entries. So I could simply compute y as a 10 by 10 matrix times my v. But if you do that, you're not going to go very far with your score in the homework, because I told you that this matrix has a lot of structure and we want to exploit it. So instead of writing this matrix like that, we want to decompose it. We want to decompose it how? Well, we want to write this matrix as 4 successive matrices. 4 successive matrices, P, that thing with the Kronecker, D, that thing with the Kronecker, so this thing here, V is here. And how are these things, where do these things come from? Well, they come from the recursive formulation where I have some P. So let's say that I want to divide this f of 10 as maybe in terms of f2s and f5s. Okay? Now what I'm saying is, what happens if I say my 1D FFT of a vector and 5, but my vector v is not 10, is not divisible by 5. It's not a multiple of 5. Then what I'm suggesting is to add numbers here until I get to a multiple of 5. Why 5? Because that's the input. I could have said 7. And then you say, okay, is v a multiple of 7? The length of v, is it a multiple of 7? If it is, fine. If it's not, you start adding zeros. This means padding. until you get to a multiple of 7. All right. Here I limit the range of P. This is totally useless. If P went beyond the square root of n, you would simply have that m over P is between 1 and the square root. So it just doesn't matter. And here are the important rules. No matrix of size n by n can be used. What I'm trying to do, I'm helping you guys, I'm telling you, don't even attempt to form those matrices. Don't try to form a big matrix and then do matrix vector product. That's not the way to do it. This is the same thing. Don't use Kronecker. Kronecker is used to define the matrix. You should not use it to solve the assignment. And then if you want to use D, P, or F, you can write them on your own, by yourself. Maybe you don't want to write the matrix. Maybe you just want to implement what they do in your code. Anyway, F, at some point you need an F as a base case. So we started from F10, and now we are decomposing F2 and F5. So what are the F like? And we can go back. Look at that. Here I defined F. Wow. Wow. I defined F, didn't I? So you know. And by the way, not only did I define it here, I define it again here. And also I told you what it is like in Matlab. So there are a number of ways for you to terminate the recursion. That answers your question, right? Yes, time for questions.
Just want to triple check. It's okay if we use Matlab's FFT function.
For the recursive case, yes.
On the bottom it says if I write functions dp and f, and when I submit it, they want me to put it in the same file.
Yes.
But obviously then it won't be able to run.
Yes, it will able to run, because I said last time that the functions, if your my1d FFT requires some local functions, you can add them in the same file, and they will be accessible only to that guy over there. So it will run. Okay? All right? So if you think that this was difficult, now we go to 2D FFTs. This is the second part of the assignment. Now we got bored with vectors and we move on to matrices. Now the input is not a vector anymore, but it's a matrix X, which, by the way, can very well be an image. And what you want to compute is, what you want to do is to compute the two-dimensional FFT of an image. To simplify your life, here I set the P parameter to decompose the F matrix, the Fourier matrix, to 2, which is the simplest case. So over here, I have already showed you what this object here looks like. I have substituted f of k with 2, k equals 2, and this is what the result looks like. Why? Because FFT of, because the FFT, the F matrix of size 2, looks like 1, 1, 1, minus 1. Then over here, we have identity, identity, identities, minus identity. Okay? All right, I don't want to go further. Once again, you want to write smart and elegant code. I give you a hint. The hint is here. Start from X and start going from the center towards the sides until you reach something like this. And at which point you make an effort and you don't use Kronecker and you do something clever instead. And it's really not as difficult as you might think it is. In fact, it should remind you of something that you have done already. Enough hints. Okay. Then, for the third part of the assignment, I want to give you a small demo. Let's see if it works. So, what I want to do is, I want to show you how to go from a function to the frequency domain, which means how to compute a fast Fourier, how to go from a function to its fast Fourier transform, how we manipulate the frequencies of these functions, and then we go back into the function space. And then you will do it as a third problem in the assignment. Okay, let's edit my FFT. What? I added my FFT already? Okay, this is clearly not what I want. Where is this coming from? So edit something else, FFT PolDJ. Okay, what do I want to do? First of all, I have to create a signal. I have to create a function. I want something periodic, something simple. So let's say we take 100 points and we build lin space between 0 and 2 times pi. Okay, so I am creating 100 points between 0 and 2 pi. And now I create my function, so my vector, sine of p. Let's see what I've done so far. What? What? Ah, thank you. Thanks. It's a good start. Okay. The plotting capabilities of Matlab there will be a lecture later on. By the way, I'm done with Matlab. We are done with Matlab. So from now, the rest is going to be just visualizations in Matlab, but I'm not sure when. So you shouldn't be preoccupied if you don't know what I'm doing here. This is to close all the windows so that every time it pops up. Now I want to build something more interesting. Let's add some higher frequencies. So maybe something like what I'm doing here, I'm mimicking sine of 30p. 30p means something really, really with high oscillations. Here we go. And let's add something, keep doing it. Let's add something more. 0, 4, sine 40p. Okay. Later. So this will be our function. Now I want to compute the fast Fourier transform of this object, which means I want to see if I can identify the wave components that are used in this signal. How to do that? Well, it's very simple. I compute the FFT of this thing. FFT of V. What is F? It's a what?
This previous FFM.
This. No, I'm saying this output, what it will be? What will it be?
A vector of complex numbers.
Very nice. How long?
As long as V.
So 100. Okay. So since it will be a vector of complex numbers, for now, I'll just show you. Here it is. This is the vector. Okay. I went down to 10, not to print too much stuff. We have seen it. See it, it's complex numbers. Okay. We have seen it. Now we forget about it. We go. But now maybe we want to look at it, so let's plot it. Unfortunately, it's complex numbers, so let's plot the absolute value of these complex numbers. What I'm doing, I'm plotting the magnitude of this vector here. Thank you. So this is to open a new figure. And here we go. So it identifies that there is one major frequency, probably two of them, and then there is something very small. So first of all, let's start doing maybe we can leave this alone. Then we say this is to create multiple plots inside the same window. So what I want to do now is shift of F. Okay, so on the what I'm defining subplot 1, 2 means I'm defining two plots side by side, and one means I will write in the first. That's what the first plot does. And then subplot 1, 2, 2 means I will write in the second, and that's what I do there. And basically, I'm plotting the Fourier transform, then some shifting, and the result. And where is the other plot? Okay, it's not there. Okay, what I've done, I have shifted the low frequency to the middle. Remember that this, maybe I didn't say it, this is a periodic thing, so these two things are actually wrapping around. So it's more convenient to shift them to be at the beginning. Assume that the origin of your frequency space, it's here in the middle. So these are low frequency, and as we grow, as we move along in the axis, we encounter lower and lower frequencies. And we can already see that we have something really strong and two smaller frequencies. So the FFT perfectly captured the fact that our function contains three types of waves. A strong one, and then you see that this one is much smaller in intensity, and this is even smaller, and that is captured by all of that.
But the small ones are with higher frequency.
Yeah, higher frequency.
Because it said smaller frequency.
Higher frequency, sorry, yes, higher frequency. And you see 40, it's clearly very high frequency. 1, it's a very low frequency. Okay, so the FFT did its job. Where it is? It identified the components of the signal. Now we can operate in this space. We can do some maybe filtering or maybe compression. In this particular case, I will try to drop these objects here to see if I can go back to the sign without the high frequency noise. How do I do that? Well, I can say t equals 5. So f1 to t equals 0. So I'm killing this part of the spectrum, and then now I'm killing this other part of the spectrum. The first 5 entries, the last 5 entries. Okay, and I could probably plot the result. By the way, so I have the original. Did I kill anything? No. A tiny bit. Okay, let's kill a little bit more. All right, I killed something, right? All right, let's see what we can do with it. Now we do some inverse FFT shift, and then inverse FFT. Now, can anyone imagine some problem that will pop up at this point? Now I would like to be back in my time domain, let's say, in my original space, and I would like to plot this signal V back. Can anyone predict some issues?
So as you cut something, so it cannot be reconstructed.
That's for sure it cannot be reconstructed, but I don't want it to reconstruct it. That's exactly the point. I want to do some changes, and I want to go back and obtain something that is not exactly the same in a way or another. Yeah?
We will get complex numbers again.
Precisely. We started with a real value function. We did some operations, some massaging in the complex world, and now we go back to the input domain. No chance we will get real numbers. So let me show you what VBAC looks like. Now we have complex numbers. So it's not going to be nice to treat them. So what I will do is to plot just the real part of VBAC. What's happening here? That's not what I wanted. Okay, we don't really see much of a difference. So let's try to kill a little bit more. Let's kill this guy too. Aha, now it looks better. So But as you can see, we didn't really kill everything. So let's remove those frequencies too. Look at that. And this reconstructs beautifully the sign over here, and we have discarded these components altogether. Now I can give you more of an idea of what your assignment is like. Let's plot a bunch of low frequencies instead. Okay? This is in the spirit of what you want to do. You start with a function. Now we have some low frequencies. And what you do is to kill a really large part of the spectrum. I think, how many did I kill? 25 and 25. So if that is the case, it means that I annihilated half of the spectrum. So actually, my vector that had 100 numbers ended up having only 50 numbers. But guess what? The resulting function looks exactly the same as the original one. So I compressed my signal, my function, by a factor of 2, and I have lost absolutely no quality. Did you get that? Anyone thinks that this is so freaking cool?
Well, the thing is, it's abhängig dependent on the input.
Absolutely.
It's
So,
like frequencies. That's the reason why.
absolutely. So what your assignment is like is to play with these with images. And I still have to decide. Maybe I will put up some high definition images on my website. You compute the FFT, the two-dimensional FFT transform. You remove the high frequencies, so your image actually decreases in size. Then you go backwards. You compute the inverse FFT. You plot the image, and you see that it's going to look exactly like the original one, but it's going to be compressed. And this is one of the really basic algorithms for image compression. So this worked. Yeah.
I have a small question.
Yeah.
What's the difference between real of a complex world and abs of complex? Well, normally I would say it's not the same. But you just use it first, and I wonder.
Yeah, it's a trick because I know how to get the solution that I want. If you plot the abs, really bad things happen. I think this is teaching by examples. Abs, there is no negative part anymore. This is seriously bad for us. Where is my eraser? Here. So real simply looks at the real part of a complex number, ignores the complex value component altogether, the imaginary component altogether. Abs adds them together to find the magnitude of these things. So it does x squared plus y squared, but then there is the imaginary. So actually, it's like that. I think it's like that. I'm not sure. But what this means is that you're killing everything negative. So that's why I didn't even look at this. So in an image, let's look at the assignment. This is part 3 of the assignment, image compression. That's it, by the way, see? 4 out of 5. the last one is how to submit. So, okay, you have to find to write a function drop that takes an image, two-dimensional array image, as input and the real number. There. I think it's better if I just show you on the board first. So you have drop. Drop takes an image, doesn't have to be square, and it takes a value k. K is between 0 and 1. What does your function drop do? This thing is called M. It goes from M to its 2D FFT. So from this image, we go to another image, but it contains the frequencies of this thing. Oh, I probably should have put it in the slides. 2D FFT of a matrix is the same as 1 F of one DFFT of all the rows and FTFFT, one DFFT of all the columns. So it's the same as FFT from left followed by FFT from the right, or it's also the same as I have to add this to the slides. So 2D FFT is the composition of two stages of one DFFT. Okay, so you start from your image, you go to the frequency domain. Then you have your number between a 0 and 1, and that number, what it does, it tells you along this diagonal, or along actually any other axis, it doesn't matter, it tells you where you are. So if 0 is here, you're exactly the center. If you're 1, you're up here. If k is a half, you are here at half. So this would be k equals 0.5. Okay, and what do? You build a rectangle that has the same aspect ratio as the image, and you kill everything outside of the rectangle. Kill means annihilate, means you set it to 0.
This is on the shifted FFT.
Thank you. So you do FFT, then you shift. Why you shift? Because the shift will put all the low frequencies here in the middle. So the important components of the image remains untouched. You kill everything outside. Then you do back shift, I shift. Then you do I to the FFT. And you go to another image. And the image, if k is small, the image looks nothing like what it was. If k is large, the image looks pretty much identical.
By image, you mean picture?
Picture, yes.
And how do you go from picture into the function?
A picture, an image is a 2D array. This is not entirely true. a black and white picture is a 2D array. So this is the part that I didn't write yet. Over here, I add, and I commented out, a set of instructions on how to read an image and what to do if you don't have a black and white image but a color image. If you have a black and white image, actually you really have just a two-dimensional matrix where each pixel is a grayscale, so it's a number that goes between, let's say, 0 and 255. So there is a one-to-one correspondence between image and the matrix. If you have a JPEG, for instance, things become more complicated because now you have colors and even intensity. So you have 4 different layers. At that point, if you want to play the color game, you have to do everything that I described for each layer. So for the RGB, for the whatever, and the intensity, and then you have to put things together. So either you guys play with a black and white image, or if you want to go fancy, you play with color, but then you have to apply the process to the 4 different layers. Okay?
Black and white is sufficient.
Sorry?
Black and white is sufficient.
Black and white is sufficient, yes. And I have not posted the assignment yet. I will put down the Matlab instructions to read an image.
So we write a function and we can use these built-in functions.
Yeah. You can use these built-in functions. FFT2 is a MATLAB's 2D FFT. FFT shift, doesn't matter, works for 1D or 2D. Inverse FFT shift, inverse FFT2.
FFT2 is the same as the algorithm we should program in program 2, right?
Absolutely.
Okay. So we don't use our own algorithm for program 3, but intern.
If you want, it doesn't make any difference. If you want, you can use your own. I didn't want you guys to get stuck here and use that as an excuse not to do that. All right?
I have another question.
Yeah.
Why are the low frequency important and not low frequency with high amplitude?
Well, this is more of a philosophical question, but the low frequencies are those that carry the most, the largest amount of information. If you think about, for instance, what we did before, the behavior of the function was given by the first sign, and then the details were given by the high frequency. So the high frequencies are those that are really detailed, that really set 2 images apart, but the main components, the knowledge is given by the low frequencies. The steps involved, oh yeah, sorry, they're here. Actually, I wrote down here.
I mean, actual examples.
The actual what?
I mean, would it be possible to put examples? So using
Examples as in pictures or examples as in what?
numbers and everything?
You mean for this?
Yes.
Well, you should probably compare against MATLAB's FFT or FFT2. So 1D FFT, there is MATLAB's FFT. 2D FFT, there is MATLAB's FFT2. So that's how to compare. Yeah.
There was said before something like problem number 1, we can use somewhere FFT, Matlab's FFT?
Well, what I'm saying is that you can use it for the recursive calls. You cannot use it to solve the problem. The problem, you have to use the recursive formula. Must be computed by the recursive formula. For the recursive, I'll see.
You won't give us the vector v.
No. You just define it yourself. Random numbers are perfectly fine. I'll see you on Thursday. No. Deadline. Sorry. Next slide. Thursday. Next Thursday. Not this Thursday. Next Thursday. So you have 9 days. I will try my best to post this tonight or tomorrow. 2 people, file names. Team names in the subject and in the files that you send. I want to receive 3 files, okay? 3 files are my 1 DFFT, my 2 DFFT, and drop. See you guys.